I'm Mike Schnecker. In many applications involving pulsed RF carriers, one is interested in the relative timing between two pulses. These applications include things like radar, direction finding, and even keyless entry systems, to just name a few. And in these systems, we typically have multiple antennas, and what we're interested in knowing is the positioning of two RF pulses relative to one another. In order to simulate this setup, we're going to use a signal generator generating a set of two different simulated antenna signals with RF pulses being transmitted in them. The instrument we're going to use to do the analysis here is the Rohde and Schwarz Rtp oscilloscope. The Rtp oscilloscope has an 8 gigahertz bandwidth on 4 channels with 20 gigasamples per second sampling rate, very fast update rate, and an advanced digital trigger. These features allow the accurate measurement of RF pulses and the analysis of those signals, including, for example, what we'll show here, which is going to be the positioning of pulses. And so the signal is being generated by a Rohde and Schwarz SMW200A signal generator. We have 2 pulses coming out of the 2 RF outputs of the signal generator being applied to channels 1 and 2 of the oscilloscope. And we're viewing the signals here on the screen. And as you can see, there's a yellow trace, which is the, let's say, antenna 1 signal, and the green trace is the signal from antenna 2. And as you can see, they're moving relative to one another. This is being simulated in the signal generator. In addition to moving the relative position of the pulses, which you can see, you also can see that the amplitudes are varying up and down. So there's actually large pulses and small pulses. This is also being done intentionally within the generator. And we're essentially trying to simulate 2 different sources of signals, one near and one far, for example. The triggering is a very important part of this measurement, and the Rohde and Schwarz Rtp has a digital trigger which allows us to trigger on the RF envelope of the signal very accurately and with very high sensitivity. And so right now we have the trigger level set fairly low in amplitude, and so we're able to capture all of the different pulses. But if we want to do a measurement, let's say, of the larger amplitude pulse, then what we're going to want to do is set the trigger such that it only captures the higher amplitude signal. So I'm going to increase the trigger level, and as I increase the trigger level up to a higher point, it's going to only respond to the larger amplitude RF pulse coming in channel 1. So as you can see now, the instrument is only triggering on the larger of the 2 different amplitude pulses. So we can follow now that RF pulse along with its associated replica in channel 2, which is now coming onto the screen, as you can see, and it's moving kind of consistently towards it as a moving target might do, for example. So what we would like to do is we'd like to measure the delay between these 2 pulses. And again, since we're really interested in the envelope of the pulse for this particular measurement, we're going to use a math function to compute the envelope of these both RF carriers and do the measurement and display on those envelopes. So what I'm going to do is minimize the 2 RF signals, channel 1 and channel 2. And so they're both now sitting off to the side here. And so now you see the 2 envelope waveforms, both in a dark blue, which is the channel 1 envelope, and a light blue, which is the channel 2 envelope. You can also see there's some what looks like noise spikes on the envelope. Those are actually intra-pulse modulation that is purposely applied to this signal. In this case, we're actually using a Barker sequence to modulate the RF carrier within the pulse. And so that modulation shows up as an amplitude variation at certain points in time. And you can see it's consistent on both pulses. To make it a little bit easier to see, we're going to actually overlay the 2 waveforms on top of each other. So now you can see both the channel 1 and channel 2 waveforms standing on top of each other. And the measurement on the bottom here is the delay between the 2 waveforms. Now, one of the types of measurements you might want to do, you might want to see how the delay varies over time, which would kind of give you an idea of the trajectory of perhaps a target that's moving, whether it's accelerating or just going at a constant rate. And so we can turn on a function within the measurement called long-term trend. And the trend allows you to display a parameter as a function of time. So now I'll turn on the long-term trend. And so we'll go into the measurement menu and enable that trend function. So now that is turned on, and we're now displaying on this purple chart the variation of the delay between the 2 pulse envelopes that we've computed versus time. And so it's going to take a little while for this to build up. We're looking at a sort of a pulse-to-pulse type measurement, and every time the instrument updates the screen with a new set of acquisitions, we're going to plot the delta. And right now, there's not much of a difference, but just now the other pulse came on the screen, so you can see it walking towards the channel 1 pulse, and you can see it tracing out a linear trend as the thing approaches. Now, this is not the best we can do because we're actually updating the screen here fairly slowly because there's a lot of measurement and processing going on after each acquisition is done. One way to improve on this and get a better picture measurement of the trend is to take advantage of our high-speed history mode. So I'm going to go into the horizontal menu. I'm going to select what we call fast segmentation mode. This is a fast segmented memory. And so the instrument will store consecutive acquisitions in memory locations after every pulse is captured. And these acquisitions can be as close together as 300 nanoseconds. So you can capture real-time data from virtually any RF system that's pulsing. So we're going to set this to acquire 1,000 acquisitions consecutively, and I'm going to enable that output. And so now what happens in this setup is we're going to acquire the memory full of 1,000 acquisitions, and once the acquisition is done acquiring those 1,000 pulses, we're going to play that back. So we close this menu and we'll be able to see the trend of the measurements. So now in the purple trace again, we're looking at the trend of the delay between the two pulses. And as you can see, it's a linear change. So this indicates that the target is moving at a constant speed across the antennas in this case, at least the simulated target is. So here we have a very powerful tool for analyzing the delay between pulses. And if you recall, we were able to use the digital trigger to selectively measure a particular set of pulses out of a mixed pulse train of different amplitudes and get very accurate measurements. So this is a very powerful tool for doing analysis of pulsed RF signals and an example of how the technology in the new Rohde and Schwarz RTP can be used.